In this lecture, we prove a convergence criterion for the numerical method called the Gauss Seidel method that is used for approximating the solution to a system of linear equations. Suppose that the system of equations is given by the matrix equation A times x equals b, where A is an n by n real-valued matrix, x is a vector of n unknowns, and b equals a real-valued n-dimensional constant vector. The Gauss Seidel method starts with an equivalent matrix system of the form x equals c times x plus b star, where c is another n by n real-valued matrix, and b star, like b, is a constant real-valued vector. Let S be the unique solution to the system of equations so that A times S equals B and S equals C times S plus B star, so that the vector S is a fixed point of the Gauss Seidel recursion. Let uppercase Y sub m be the real valued estimate for S, obtained at the mth iteration of the Gauss Seidel method. Then, for the next vector estimate, uppercase Y sub m plus 1, to find the first component of the vector y sub m plus 1, or to find the new lowercase y sub 1, we multiply the first row of the matrix C to the vector y sub m to get this string of terms. Then we add b sub 1 star. For the second component of y sub m plus 1, or the new lowercase y sub 2, we take c sub 2 1, but rather than the old y sub 1, we multiply to it the new lowercase y sub 1 that we had just obtained. Then we use the old values of the rest of the components of the vector y sub m to get this string of terms. Then we add b sub 2 star. We generalize this for the rest of the components of the vector y sub m plus 1. We will prove this theorem or convergence criterion for the Gauss Seidel method in this video. Suppose that for every row I of the matrix C, the sum of the absolute values of the components of row I is less than 1. Then the sequence of vector estimates y sub m will tend to the exact solution S as m tends to infinity. Since the matrix C has a finite number of rows, the maximum of all these sums should be less than or equal to some constant k, which is less than 1. This maximum sum is the norm of C. That is induced by the infinity norm of x, which is given by the maximum absolute value out of all the components of x. In order to prove the theorem, we will first show that the Gauss Seidel recursion can be written as an affine transformation. We split up the right side of the recursion equations into three parts. The first part is a matrix product involving the components of the vector y sub m plus 1. These are the new lowercase y sub i's. Extracting the coefficients of the new y sub i's, we have a lower triangular matrix times the vector y sub m plus 1. The second part involves the components of the vector y sub m, or, this time, the old y sub i's. This part can be written as the product of an upper triangular matrix and the vector y sub m. The third part is some real-valued n-dimensional constant vector b prime. B prime is not B star, since the components of B star are also involved in multiplications with the C sub ij's. For example, for the new y sub 2, we have the constant C sub 2 1 times the new y sub 1, which involves B sub 1 star. This product is added to B sub 2 star, giving us B sub 2 prime. Let the components of the vector B prime be lowercase b sub I prime, where I goes from 1 to n. We call the lower triangular matrix uppercase L, and the upper triangular matrix uppercase U, so that we have this matrix equation for the Gauss Seidel recursion. The left side is just the identity matrix times the vector y sub m plus 1, so that moving this y sub m plus 1 term to the other side, we get this matrix equation. The identity matrix minus the matrix L is lower triangular. In fact, for the entries of the identity matrix minus L, the entries of L change signs by acquiring minus signs. while the diagonal entries are all ones from the identity matrix. As a result, the determinant of the identity matrix minus L is 1. Because being triangular, its determinant is the product of the diagonal entries, which are all equal to 1. And since its determinant is not equal to 0, the identity matrix minus L is non-singular or invertible. We multiply the inverse of the identity matrix minus L to everything in this equation. And so y sub m plus 1 equals the product of the inverse of the identity matrix minus L, u, and y sub m, plus the inverse of the identity matrix minus L times b prime. We call this matrix product the matrix D. We call this matrix product the n-dimensional vector b double prime. Therefore, the Gauss Seidel recursion can be written as an affine transformation. We are going to start ignoring the vector b double prime, since b double prime ends up being inconsequential, as we shall see later on. Let X be a general vector in n-dimensional real space. We apply the recursion equations to X, sans b double prime, to get the following recursion equations for X. These components are the components of d times X. Our immediate objective now is to show that for I equals 1 to n, the absolute value of the ith component of d times x is less than or equal to k times the norm of x. This implies that the norm of d times x is less than or equal to k times the norm of x. We prove this by mathematical induction. For I equals 1, applying the triangle inequality to this equation, the absolute value of the new x sub 1 is less than or equal to the left side, where we apply the absolute value to every term. Each x sub I absolute value is less than or equal to the norm of x, since the norm of x is the maximum absolute value of all the x sub i's. The sum of the absolute values of the c sub ij's is less than or equal to k, so that factoring out the norm of x, we find that the absolute value of the new x sub 1 is less than or equal to k times the norm of x. Hence, the claim is true for I equals 1. We now assume that the absolute value of the new x sub I is less than or equal to k times the norm of x for I equals 1 to j for some j greater than or equal to 1 and less than n. We are going to show that the absolute value of the new x sub j plus 1 is less than or equal to k times the norm of x. The new x sub j plus 1 equals the sum of the terms involving the just obtained new values of x sub I, where I goes from 1 to j, followed by the terms involving the old x sub i's, where I, this time, goes from j plus 1 all the way up to n. We take the absolute value of everything in this equation. The triangle inequality says that the left side should be less than or equal to the right side. We first examine the terms involving the new x sub i's, where I goes from 1 to j. By our induction hypothesis, the absolute values of these new x sub i's are less than or equal to k times the norm of x. K is less than 1, so that the absolute value of c sub j plus 1i times k is less than or equal to the absolute value of c sub j plus 1i. And we get this inequality for these new x sub i's. For the terms involving the old x sub i's, each x sub I absolute value is less than or equal to the norm of x. And so the absolute value of the new x sub j plus 1, which is bounded above by the sum of these things, should also be bounded above by the sum of these things, where I goes from 1 to n. The sum of the absolute values of the c sub j plus 1i's is less than or equal to k. Therefore, the absolute value of the new x sub j plus 1 is less than or equal to k times the norm of x, completing the induction proof. The norm of the new x or the norm of d times x, is less than or equal to k times the norm of x. We can also conclude that the norm of d is less than or equal to k. We leave the details as an exercise for the viewer. The viewer can also show us another exercise that the norm of the matrix D is less than or equal to the norm of the matrix C. Now let the error vector at the nth iteration be uppercase E sub m. We define E sub m to be the solution vector S minus the vector estimate y sub m, so that E sub m plus 1 equals S minus y sub m plus 1. S equals D times S plus B double prime, since S is a fixed point of the recursion. Y sub m plus 1 is D times Y sub m plus B double prime. B double prime, as promised, just cancels out. Hence, E sub m plus 1 equals D times the quantity S minus Y sub m, or D times E sub m. Therefore, the norm of E sub m plus 1, which is also the norm of D times E sub m, is less than or equal to k times the norm of E sub m. Since k is less than 1, the sequence of the norms of the E sub m's can be compared to a geometric sequence with a non-negative common ratio that is less than 1. And so the sequence of the norms of the E sub m should tend to 0, and that the sequence of error vectors E sub m should tend to the 0 vector as m tends to infinity. Therefore, the sequence of vector estimates y sub m should tend to the exact solution as m tends to infinity.